Welcome back to the deep dive. We spend so much time talking about the what of technology, the shiny new apps, the big AI breakthroughs.
Mm-hmm.
But today, I want to get into the how, the invisible architecture that basically keeps the modern internet from just collapsing under its own weight. We are talking about microservices.
And it's the architectural style that's really defined the last decade of software engineering. But it's funny you mentioned collapsing because that's the whole story right there.
How so?
Well, microservices solved one massive problem, but in doing so, they created a whole new set of headaches that, honestly, engineers are still trying to figure out.
I was going through the research packet you sent over,
Yeah.
and I have to say, it sounds exhausting.
It can be.
It really feels like we took something simple, shattered it into 1,000 pieces, and then dared ourselves to put it back together again.
That's great. Well, that's a pretty good description, actually. But to see why we did it, you really have to look at what came before it. The monolith?
Right. The big block of code.
Exactly. I mean, think of the monolith like a medieval castle. It's one giant fortified structure.
Okay.
Everything's inside the same walls. The kitchen, the barracks, the throne room. It's solid. It's secure.
But if you want to expand the kitchen,
That's the problem. If you want a bigger kitchen, you might have to knock down a load-bearing wall that's holding up the king's bedroom.
and in software terms, that means you change one line of code in the, I don't know, the shipping module.
And suddenly, for no logical reason, the user login breaks.
Because it's all one big tangle of wires,
Yeah.
tightly coupled.
Exactly. So the industry shifted, we moved to microservices, and instead of a castle, you should think of a city.
A city.
Yeah. You have a bakery, a police station, a library. They're all separate buildings if the bakery catches fire.
The library doesn't burn down.
Right. It sounds safer. And the biggest benefit really is speed.
Independent deployment. That's the holy grail, right?
It is. The team running the inventory service can push an update on a Tuesday morning without even talking to the payment service team.
They just renovate their one building. They don't have to redeploy the whole city.
You got no more deployment day where everyone just holds their breath and hopes for the best.
Okay, I get the appeal. I really do. But this is where I get a little skeptical.
Go on.
In a castle, if I need to go from the kitchen to the throne room, I just walk down a hall. But in a city, I have to get in a car, drive through traffic, find parking.
You have hit the nail on the head. That is the trade-off.
So we traded one problem for another.
We traded code complexity, the spaghetti inside the monolith, for network complexity.
Yeah.
Now you've got hundreds of services that all need to talk to each other over a network.
And networks are unreliable, they're slow, they break.
So today, we're not really talking about the services themselves. We're talking about the glue, the infrastructure.
The things that stop this city from turning into total anarchy.
We call them artifacts, the roads, the traffic lights, the maps. Without them, microservices are just a disaster waiting to happen.
Okay, so let's start at the front door. I open a shopping app on my phone. On the back end, there are maybe 50 different services running.
Easily 50, probably more.
User profile, recommendations, cart, search. So does my phone have to make 50 separate phone calls to 50 servers just to load the home screen?
No, God, no. That would be incredibly slow.
And my battery would die in an hour.
Right. This is where our first major artifact comes in, the API gateway.
The receptionist.
Think of it more like a high-speed dispatcher. Your phone sends one single request to the API gateway.
Okay.
The gateway then turns around and fires off those 50 requests to all the internal services, probably in parallel. It collects the answers, stitches them together, and sends one nice, clean response back to you.
So it hides all the mess.
It creates an abstraction layer. It's called request aggregation, but it also does something else that's absolutely critical. It handles cross-cutting concerns.
Fancy term. What does that mean?
It means things that every service needs to do, but nobody wants to build twice, like authentication. You don't want the cart service team and the search service team to both have to write code to check if you're logged in.
You do it once at the gateway.
Exactly. SSL termination, rate limiting, it all happens right at the front door.
Okay, but let me play devil's advocate here.
Please.
If we broke up the monolith to avoid a single point of failure, didn't we just create a new one? If the API gateway goes down, the whole city is closed, right?
That is a very real risk, and that's why gateways are usually highly clustered and redundant. But yes, you are putting a lot of eggs in that one basket.
But the alternative is worse.
The alternative is exposing hundreds of little services to the public internet, which is just a security nightmare.
Fair point.
Okay.
Okay, so we're through the front door, now we're inside the network. And this is the part that just boggles my mind.
The where is everyone problem.
Yes, In a traditional setup, I know the database is at this IP address, it stays there, but in the cloud, things are ephemeral. Servers spin up, they crash, they move.
IP addresses change constantly.
So if I'm the order service and I need to talk to the inventory service, how do I know where it is right now?
You can't just write it on a sticky note. You need service discovery.
A dynamic phone book.
Basically. But keeping that phone book up to date is unbelievably hard when you have thousands of services appearing and disappearing every single minute. Which brings us to LinkedIn.
Oh, I love this case study. Because LinkedIn isn't just big, it's enormous. This is a scale where normal tools just break.
They were running into a wall. For a long time, they used a system based on Apache Zookeeper to keep track of where everything was.
And Zookeeper's a classic tool for this, right?
It is, but its design has a fundamental problem at that scale. It's designed for consensus. It wants to make sure everyone agrees on the absolute truth.
And that takes a lot of coordination.
A lot of chatter between servers. So when LinkedIn grew to hundreds of thousands of instances, Zookeeper just became this massive bottleneck.
It's like trying to get a committee of 10,000 people to agree on where to go for lunch.
And everyone is hungry and yelling at the same time. So LinkedIn did something radical. They just threw out the whole consensus model.
And moved to what?
An event stream model using Apache Kafka.
Kafka.
Yeah.
It always comes back to Kafka.
It's built for these high-throughput data streams. It's fire and forget. So when a new service starts up, it doesn't try to get everyone to agree. It just shouts into the Kafka stream, "Hey, I'm here. I'm at this IP."
And who's listening?
They built a dedicated component called the Observer. The Observer's only job is to read that stream of shouts and update the map for everyone else.
So they separated the writing of the map from the reading of the map.
Precisely. They decoupled the problem. But here's the really crucial technical detail. They started using the XDS protocol to broadcast these updates.
XDS. Sounds like a sci-fi weapon.
It stands for Discovery Service. It's basically a universal language for infrastructure, popularized by the Envoy proxy. It lets the Observer push updates to the whole fleet in near real time.
So it's not a committee meeting anymore, it's a live broadcast.
And that one shift allowed them to scale from thousands of nodes to millions. It just removed the coordination bottleneck entirely.
That's amazing. Okay, so we can find each other now. Let's talk about the data, because this is where most microservice projects fail, isn't it?
The data problem, yes. Because of the golden rule.
Database per service.
Yes. You should not share databases between services. It's a strict rule.
Which, again, to an outsider, just sounds inefficient. If I have a user database, why can't the order service just peek at it to get my address?
Because if the order service is reading directly from the user database and then the user team decides to change a table,
The order service crashes.
coupling, you're right back to the monolith. So you split them, but now you've created data silos.
User data in Postgres, product data in MongoDB, logs in S3.
And then the boss walks in and asks for a list of all users who watched a sci-fi movie in the last week.
In a monolith, that's one SQL query. A simple join.
In microservices, it's a nightmare. You have to query one service, get a list of IDs, then query another service for every single one of those IDs.
Yeah.
It's slow, it's error-prone.
Which brings us to Netflix. They had exactly this problem. They needed to see the whole picture of a user to make good recommendations.
They needed a graph. Node A, the user, is connected to Node B, the movie, by an edge, which is watched.
So I just assumed they went out and bought a massive graph database, like Neo4j or AWS Neptune.
Yeah, I looked at them, but you have to remember Netflix's scale. Billions of nodes, hundreds of billions of edges. The off-the-shelf graph databases at the time just died. They couldn't handle that kind of volume with the speed Netflix needed.
So they built their own. But reading about it, it sounds like they kind of cheated in a really clever way.
Cheated is a strong word. I'd say they emulated. They built the real-time distributed graph, or RDG. But underneath, it's not a true graph engine.
It's a key value store, Cassandra.
Yep.
How does that work? A key value store is just like a locker, right? You have a key, you open it, there's stuff inside. How is that a graph?
So imagine user X has a locker. Inside that locker, Netflix stores a list, an adjacency list. And it's literally just a list of the IDs of every single movie user X has ever watched.
Okay.
So if they want to know what did user X watch, they don't have to traverse some complex web. They just go to Locker X, pull out the list, and boom, there are all the edges.
That sounds incredibly fast for reading data.
It is blisteringly fast. Constant time complexity.
But what about writing? Every time I finish an episode of a show, they have to update that list.
Yeah.
And there are millions of people doing that at the same time.
Kafka again.
Of course.
It always comes back to Kafka. Every play event is a message on a stream. The RDG consumes those messages and just appends the new movie ID to your list in the key value store. It's eventual consistency.
So it might take a second to show up.
Which is totally fine for a recommendation engine. They stripped away all the complex graph features they didn't need and just built the one thing they did need on top of simple, scalable storage.
That's so clever. Okay, so that's data. But what about actually doing things? Heavy lifting. I'm looking at the Pinterest case study now.
Ah, async processing.
Right. Because when I click save on a pin, it feels instant. But in the background, Pinterest is freaking out.
Oh yeah, it's huge cascade. They have to notify your followers, resize the image for 5 different screen sizes, scan it for spam, update the ad engine.
If they did all that while I was staring at the screen,
The app would hang for 10 seconds. You delete it.
Yeah.
So they put all those jobs in a queue. Hey, do this later,
and their first system for this was called Pin Later.
which was a great name, but it ran into a classic engineering nightmare. Lock contention.
I love this concept. It's like a crowded bar.
That's a perfect analogy. Imagine a bar where the bartender, the database, has a list of orders, and you have 1,000 waiters, the workers, all shouting at the bartender at once. Do you have an order for me? Do you have an order for me?
And the bartender spends all their time just answering no and never actually pours any drinks.
That is lock contention. The database CPU hits 100% just managing the workers. It's totally gridlocked.
So they rebuilt it as Pacer, and the key innovation was adaptive sharding. This was the part where I had to read the notes twice. Why is this such a game changer?
Because not all queues are created equal. Think about it. If I pin a photo of a lasagna, maybe 3 people get notified. The queue is tiny.
But if a huge celebrity pins a lasagna,
Millions of notifications. The queue is massive. In a normal system, that massive queue would sit on one database shard, and that shard would just melt down. It becomes a hotspot.
so adaptive sharding spreads the pain.
It detects the volume. A small queue stays on one shard. But if a queue is massive, Pacer automatically spreads it across huge chunks of the cluster. It levels the playing field.
And they paired that with worker isolation.
Which is just smart resource management. They use Kubernetes. And they realized resizing an image takes a ton of CPU power. Sending a notification takes almost none.
So don't put them in the same line at the checkout.
Exactly. They created high CPU pods for the images and low CPU pods for the notifications. It's like the express lane at the grocery store. You don't want the person with a full cart blocking the person buying a pack of gum.
It seems so obvious when you say it, but I bet it was a nightmare to debug before they figured that out.
Oh, absolutely.
All right, so we've covered the plumbing, the data, the background jobs, but let's bring this into the present day. Because now, we're not just serving web pages, we're serving AI.
This is really the new frontier for microservices.
Yelp Assistant case study. This uses RG Retrieval Augmented Generation, which is the buzzword of the year.
It is. But at its core, RG is really just a microservices orchestration problem.
Explain that, because to me, it just looks like a chat bot. I ask, is the patio at this restaurant heated? And it says, yes.
But how does it know that? The AI model itself doesn't know anything about that specific restaurant's patio. It has to go look it up.
Right.
But Yelp has all these different kinds of data. They have user reviews, which is just text. They have amenities lists, which is structured data. And they have photos.
So they split the data retrieval.
Exactly. Unstructured text goes into a search index. Structured facts go into a database like Cassandra. But here's the real magic. They use hybrid retrieval.
Meaning they check everything at once.
Yes. So when you ask about the heated patio, the system searches the text of all the reviews for the word heater, but at the same time, it's looking at the photos.
Wait. How does it search a photo for heat?
Embeddings. This is a core AI concept. The system turns a photo into a vector, a long list of numbers that represents the features in that image. Outdoor, metal, fire, cozy.
So the photo of a heat lamp gets converted into math that looks like the word heater.
You got it. So even if nobody ever wrote the word heater in a review, the system can find the photo of the heat lamp and infer the answer.
That is incredibly cool. But again, coming back to the architecture, searching text, querying a database, doing vector math on images, that sounds really slow.
It would be if you did it one after another. You'd be waiting 10 seconds for an answer.
Which is an eternity in AI time.
So they built another gateway pattern, a content fetching API, to fire all those requests in parallel. But the real trick to making it feel fast is SSE.
Server-sent events?
It's streaming. Instead of waiting for the AI to think of the whole paragraph and then send it to you, it sends the first word, then the second, then the third.
So as the user, I just see it typing, I think, oh, it's working.
It's the difference between psychological latency and actual latency, and it keeps you engaged.
Wow. It really highlights that AI isn't just some magic dust. It needs this heavy-duty, distributed plumbing underneath to actually work.
The AI is only as good as the infrastructure that feeds it data.
So we've built this massive city. We have the GPS, the nervous system, the gateway walls, the AI libraries. It works, but what's the tax?
There is always a tax, and the tax is observability.
Meaning?
In the old monolith days, if the app crashed, you'd go to the server, open the log file, and scroll down until you saw the word error.
Simpler times.
Now, a single user request hits the gateway, bounces to the auth service, checks a cache, hits the user service, fires a Kafka event, triggers a serverless function.
And if it fails somewhere in the middle?
You are hunting for a needle in a stack of needles that are scattered across 50 different haystacks.
So you need new tools.
You need distributed tracing. Every request gets tagged with a unique ID at the front door, and that ID has to be passed to every single service it touches. Then you use a centralized logging system to reassemble the whole story of what happened.
And if you don't have that...
You are flying blind. You literally cannot debug your own application.
Which brings me to my final thought. Maybe it's a bit of a provocation for everyone listening.
I'm ready.
We've talked about Netflix, LinkedIn, Pinterest, Yelp. These are tech giants. They have hundreds of engineers whose only job is to maintain this city.
They have the resources to pay the tax.
Exactly. But what about a startup? Or even a mid-sized company? Is all of this necessary? We're starting to see some chatter now about macroservices or the modular monolith. People are swinging back the other way.
It's a very healthy correction. I think for a while, we all did microservices because it was trendy. Netflix does it, so we should too.
Cargo cult programming.
That's the one. But if you don't have Netflix's scale, you probably don't need Netflix's complexity. A modular monolith where the code is clean and separated, but it's all deployed together, is often the right choice for 90% of companies out there.
So don't build a city if you only need a house.
Or at least don't start building the city until the house is absolutely bursting at the seams.
I think that's the perfect place to leave it. Microservices are powerful, but they are not a free lunch. You have to be ready to pay the bill.
Couldn't have said it better myself.
Thanks for listening to this deep dive. Go check your logs, and we'll catch you on the next one.